Thank you. Thank you for inviting me. I really apologize for basically missing the first 4 days of a fantastic workshop. I had my reasons. But yes, thank you all for showing up to an early morning talk. I hope it's worth your while. Okay, great. So I want to tell you about this work, which is a little bit dated at this point, but hopefully you'll still enjoy it. It's from maybe about a year ago, joint with David Steurer and Rajesh Buhai, both from ETH Zurich. I'll explain what the title means in a bit, okay? But, just to begin with, I hope all of you have heard about the problem of finding cliques in graphs. Basically, a set of nodes which are all connected to each other and as large as possible. And so this talk is really about, some version of the problem of, finding large cliques in graphs, okay? Good. So let me just, set the context for what I'm going to tell you about. So, one of the original CARP's, 70s list of like famous problems of NP-complete problems includes, maximum clique. It's a, really hard problem. Finding large cliques is hard, and in fact, it turns out to be hard in a very strong sense, which I'm just going to summarize for you because, that's all I need. So, there is an algorithm which, given a graph, which contains an almost linear size clique, can find something which is like barely polylogarithmic. And as far as we know, this is tight. So, the exact numbers, etc., is not important here. The point is that, if you were to consider the worst case model for like trying to understand how to find large cliques, think of it as like a vehicle for designing heuristics for finding large cliques, you are in trouble because, there seems to be very little room for algorithmic innovation, okay? So what do? Well, one of the predominant approaches to escape this kind of worst case, algorithmic hellhole, so to speak, is to think about better models of input instances, and this itself is a very old enterprise, basically also beginning with CARP in the 70s, and the natural formulation is often in terms of probabilistic models of instances. Okay. So the most well-studied probabilistic model for finding large cliques is this so-called planted clique problem. Again, long history. The problem is the following. You're given this time a random graph. By random graph, I mean GN1/2, where every edge is sampled independently with probability half, right? And then you add for some k a k clique to it. So it takes some k vertices, add the remaining edges to make a clique on it. Okay. And the question is, when can you find the added clique? Okay. So because a random graph does not have a clique of size too much larger than 2 log n, there is like a natural quasi-polynomial algorithm that works as long as k is much larger than 2 times log n. Okay, so that's kind of nice. But the question is, can you do better than this brute force algorithm? So the brute force algorithm in this case is really quasi-polynomial. The question is, can you beat it? Okay, and it turns out like we can beat it. But only when the added clique is of size at least some constant times square root of n, and this is like one of the first and famous instances of the use of eigenvalues for algorithmic problems. So this is a result of Alon, Krivolovich, and Sudakov from the 90s, and refinements of this result basically say that you can basically find a added clique as long as it is any constant times root n, where the running time depends, the exponent of running time depends on this constant multiplying square root of n. So if you give me larger polynomial time, I can shave off the constants in front of root n, but no better. Okay, good. So this maybe doesn't look that great of a situation, but we have reasons to believe that maybe whatever is happening here is as good as it gets, modulo some restricted assumptions, restricted lower bounds or whatever. Okay. So again, bottom line for us is that it seems like there is at least some more room for innovation algorithmically. You at least are looking at eigenvalues of graphs and able to like somehow understand interesting connections to cliques and so on. So maybe it's a little bit more optimistic from an algorithm designer's perspective. Okay, good. So, but before we get too optimistic, it's very natural to ask, are we deceiving ourselves? Okay, so whenever you choose average case model, there is always this question of, did I choose the right model? Okay, and this is more than just like a philosophical question, because it turns out that algorithms that we design in these average case settings often turn out to be rather brittle, that if you modify the model only a little bit, the algorithm completely drastically breaks, which is kind of not good because in the end it's a model that we chose, right? So just to, for example, give you a sense of what's happening in this context, there is a very simple heuristic for finding large planted clicks, which is simply like you take some largest degree vertices, and this works with like some extra root log n, when you pay an extra root log n in the size of the added click. So it can almost root n, but maybe root n log n, right? But this heuristic is extremely easy to break, right? Like I'm basically imagining that the large degree vertices only come from the click, and this is true because somehow the degrees of vertices in the random graph are very tightly concentrated. But you can imagine that just modifying some order of n edges would completely break this heuristic. It does, okay? The reason I'm saying this is because a similar thing actually breaks even the spectral method of Alon, Krivulevich, and Sudakov. So the point is that there is a sense in which the algorithms we came up with are rather brittle or overfitting to the specific random model that we have chosen. And so in some sense it is very hard to argue that we are doing interesting things algorithmically if this is all there is. Okay, so this is basically the backdrop of what I want to talk about. The natural way out is to think about like algorithms which are at least a little bit robust to the choice of the random model, like heuristics that somehow don't overfit to the specific modeling choices that we make. Okay, good. So this is not like a new focus. Today I'm talking about just combinatorial optimization like click problem, but this is basically, for example, the issues in statistical estimation, and that leads, gives rise to this area of algorithmic robust statistics, where you want your algorithms to be resilient to modeling assumptions. Similar thing goes on in like analysis of algorithms and smooth analysis. And today, I'm going to talk a little bit more about semi-random models before telling you about how we can try to get something more meaningful for the planted click problem. Okay, good. So these semi-random models, were introduced in mid-90s. In this very cool paper of Blum and Spencer, and then really developed much further in Feige and Killian's 1998 paper. And the idea is that this time, in some sense, an adversary and a benign random model will collaborate to create an instance, and with the intuition that the adversary will make it hard for you to somehow utilize the specific quirks of the random model that you have so chosen. Okay, so very crucially, the adversary in these models acts adversarially and adaptively. Like you look at the benign random choices, and then the adversary comes and like tries to poke holes in them, like tries to modify the graph that you for example, build. Okay, so such models are very well studied for a number of optimization problems, and basically form a very important thrust in this area called beyond worst case analysis. So if you've seen like this book edited by Tim Roughgarden on like this area, like kind of a compendium survey of this area, then the section 3 of this book, one of 5 sections, is entirely dedicated to semi-random models. Okay, so this is going to be of our interest today. And what I'm going to do next is tell you the semi-random model for click problem, the planted click problem that Feige and Killian came up with. Okay, again, at any point in my talk, please feel free to stop me. I don't have to complete all that I have to say. Excellent. Okay, so let me tell you the model. Like I told you, a benign random choice is going to now interact with some adversarial choices in order to develop the model, right? So here is how it works. The first step is to simply choose a planted click graph. Okay, take GN1/2, plant a click in it on some vertices. Let's say S star. S star would always be my notation throughout this talk for the vertices that I've added the click on. Okay. Now what do? Well, now the adversary enters the picture. They see the graph you've sampled, right? And they do something to it. What do? Well, they do 2 steps. They do what is called adaptive addition, which means that they can basically add any edges in this part. Okay, and then they can so notice that these red edges now remain random, but they've added like some edges here, and they can also delete any subset of edges which are not entirely contained in the click, which means that they can add and delete any edges here, which is equivalent to saying that I can basically develop whatever graph I want on V minus S star. But on these red edges that go between S star and V minus S star, the only thing they're allowed is first the random choice happens, and then some deletions happen, but nothing can be added back to the cut. Okay, so just to explain the model in a different way, this is basically what I was arguing to you. You can think of the graph as being chosen as follows. First take a click, S star, choose the edges that go out of S star randomly, like with 1/2 probability each. Then choose an adaptive worst case graph on the rest of the vertices, right? And then delete any subset of edges in this red part. Okay, so the only way you're restricted, the only reason you might not be creating a worst case hard instance is because you cannot add back edges in the cut of S star. That's the only remaining benign part in this model. Any questions about the model? Yeah? Excellent. So adaptive means that the adversary is all powerful. They look at your graph, they know your click, they know everything about the graph, and they choose the edges to plant in V minus S star and choose the edges to delete based on the knowledge of the random graph sampled earlier. They're not oblivious to your random choices. Good? Any other questions? Excellent. All right. So let's just reason about this model a little bit. You know, if I don't do any of the adaptive adversarial steps, it's of course the planet click model, so it's a generalization. If I don't do addition of edges, I only allow deletion of edges, then it turns out that this also is a model that again was proposed in Feige-Killian's paper. So they had like a string of like harsh to less harsh models of versions of planet click, and this was also a model that they proposed. It's called planet click with helpful monotone adversary, with the intuition that if you only delete edges outside of the click, you can only make the click more prominent intuitively. You can only be helping the algorithm, so that's why the monotone part, like somehow it's only supposed to help, but the question is, are your algorithms fooled by it? Notice that your degree algorithm, your spectral methods are already like very well fooled by just the monotone adversary. They don't even need like this worst case choices on B minus S star. Okay, great. So so this breaks like these two kind of heuristics, but back in the day, Feige and Krauthammer already figured out a fix. They showed like a natural SDP relaxation basically recovers the same result as the vanilla planet click problem, but is also robust to a monotone adversary. Okay, good. And today our goal is to look at like their harshest semi-random model in the same paper, the semi-random, the model that I defined for you. And the key part here is that somehow something at the outset is different about this model. In particular, in all the models that I talked about so far, the added click is basically with very high probability the unique maximum click in the graph that I've generated. In the graph now I'm describing to you, because V minus S star is completely arbitrary, S star may not even be a max click, right? Like there could be much larger clicks hiding in V minus S star, right? So in particular, like there could be a worst case hard instance of the click problem, which is very, very hard, as we saw in the first slide, encoded in this V minus S star part, right? So we could ask, what even is the goal? What do we really want to do if the maximum click is not S star, right? And so our goal would be, well, I'll give you 3 goals, and then I select the the best one, in some sense the one that implies all the others. You could phrase the question of finding a k click, where k is the size of S star. Okay, no max click, just find me a k click. Actually, I can also ask, suppose I give you some more information about S star. Suppose I give you a uniformly random vertex inside of it. Now can you uniquely tell me what S star is? Okay. And why do I need, by the way, this? Because the S star is not in principle uniquely identifiable, right? Like the adversary can simulate this S star with random edges going out of it several times in the V minus S star point. So without giving me some advice, S star is not even uniquely identifiable, right? The final goal would be to find a list of small number of clicks, and n over k, by the way, is basically the smallest you can hope for, where the k clicks are pairwise disjoint. Right? So find me a list of like, basically essentially disjoint k clicks such that one of them is guaranteed to be S star, okay? So this goal clearly implies the top 2. So this is going to be my focus, okay? So I'll basically give you algorithm for solving this goal, and which is basically my purpose for the rest of the talk. Good. All right. Excellent. So let me tell you what's known about this model. So it's maybe not so surprising, but our standard tools, for example, the Feige-Krauthammer SDP doesn't quite work. And the reason is very simple. The reason is that V minus S star could just be a worst case integrality gap instance, right? Something that fools all NP algorithms, all polynomial time algorithms, of course, will fool our SDP. So we've got to do something more, okay? So progress on, like even though this model has been around for like 20 whatever years, progress began only maybe fairly recently. So there's this very nice paper of Cheriker, Steinhardt, and Valiant, who showed that for a slightly weaker model, which I will not define, slightly weaker than what I'm telling you, they found an algorithm that works when k is at least n to the 2/3 up to some logarithmic factors, okay? And remember the vanilla planet click is solvable when k is square root of n, so this is like significantly larger than it. And then in some sense a curveball came with this Steinhardt paper, who showed that unlike the vanilla planet click problem, where at least information theoretically the problem is solvable at 2 log n, the task of finding a short list, n over k size list, is in fact information theoretically infeasible unless the click that you planted is of size at least square root of n. So there is something not just computationally but statistically changing about this model with this combination of adversarial and benign random choices.
But this doesn't rule out 1, right? Meaning finding.
This doesn't rule out one, right? Like in some sense, this is an information theoretic lower bound, so you have to pose a statistical question. One is not a statistical question, like one is basically only an algorithmic question. But it's saying, for the natural statistical question you could ask, like some identifiability type question, you are in trouble unless the clique is of size at least square root of n.
So for the list decodable, you would need to recover all of the cliques that are at least size k, or the guarantees like
in some sense, any guarantee would have to be of that sort because if I planned like equivalent models, you can't quite tell which one it was. So any reasonable algorithm, any correct algorithm will have to develop all of them. Exactly. Good. All right. So the state of the art before the work I'm going to tell you about is this paper due to Mackenzie, Mehta, and Trevisan, who showed basically in the model that we're working with today. So that's again, don't ignore the words. Works when k is at least n to the 2/3. So they shave off the log factor and they make the model a little bit stronger. And you can see that there's something weird going on at n to the 2/3. Like there are people working on this problem, but like getting stuck at n to the 2/3. And this is one thing I'll demystify. There is in principle like a natural way to believe that there is some barrier at n to the 2/3. And that's basically maybe the summary of prior work, that there is an algorithm that works at n to the 2/3, and there seems to be something weird going on, right? And I'll explain what's weird going on eventually in this talk. Okay, good. So because of like this weirdness, Feige and Steinhardt both posed this as an outstanding open question of whether this problem is as easy as the vanilla planted clique, or is there something funky going on computationally with it? And the result I'm going to talk about is basically in some sense a resolution of their question. So I'll show that for every epsilon, there is like an algorithm that runs in time n to the 1 over epsilon, and succeeds whenever the planet clique is of size n to the 1/2 plus epsilon. So the point is that as epsilon goes to 0, you are getting closer and closer. You never reach, but you get closer and closer to square root of n. There is no real barrier at root n, n to the 2/3. Any question about the result?
Does it give a list of cliques?
Say it again?
It's a list.
This would be a list of cliques, yes. Yeah, so this talk, the algorithmic guarantee I'll give is like find a list of n over k cliques so that one of them is guaranteed to be S star.
And how big is the list?
N over k. Well, okay, maybe, yeah, actually literally like something like 1 plus little o of 1 times n over k.
Okay.
But do you have so many cliques?
Well, you may not, but it's an upper bound, right? Like maybe maybe in the graph you have there is only one, right? Any other questions? Good, excellent. So let me tell you a little bit about like some comments on this result just to like appreciate it a bit better, and then I'll tell you how to prove it. Okay. So right, if you've seen like sum of squares or like heard about it in the past, this is like a way to like build stronger SDPs. It turns out that this algorithm is based on some 1 over epsilon round strengthening of the basic SDP with sum of squares. Essentially, it just means that I have an n to the order 1 over epsilon size SDP that works. Okay. Good. Again, this is a comment for people who know about sum of squares. Ignore it. Nothing is lost if you don't know this. But basically, like people who have thought about this problem know that there's a dearth of examples where higher but constant degree SOS gives you like a major win, and this seems to be like a very nice example of a problem where higher constant degree SOS gives you a win, while I'll argue in a provable sense there is no win at degree 2. Okay. So just to remind you, for the planted clique, the vanilla planted clique, there is no win by going to higher constant rounds except for like a constant factor in front of the root n. So somehow the point here is that there seems to be something interesting going on when you use higher degree sum of squares. Excellent. So again, this is for people who have worked on some other topic now. If you've like thought about like problems in robust statistics and have seen this works on list decodable learning, then the algorithmic framework that we are actually doing here is taking this list decodable learning framework and applying it on this problem. There is like one key step, which is the problem dependent thing, which is also basically the focus of the talk. But the rest of the framework is more or less black box at this point. And finally, there is a version of this result that holds for not just GN1/2 plus GNP. I won't tell you about it. And there is some evidence that beating the kind of n to the 1/2 plus epsilon kind of guarantee in the way we are doing it would require somewhat different ideas in terms of some weak lower bounds. But ask me towards the end, and I'll give you some more latest scoop on this. Good, excellent. So if there are no questions, which there can be, I will tell you how to at least think about this problem a little bit more. But let me pause and see if there are questions I should handle. Okay, very good. All right, so the model is before you. Like remember, we sample a graph, then there is adaptive addition and deletion of edges, in V minus S star, and we can delete any edges, not in the clique, but in principle also in the cut, right? But we can't add edges to the cut. That's the model. Okay, good, excellent. So here is the plan for today. I'm going to give you like a very inefficient algorithm, okay? And then, I will identify like a key property of this inefficient algorithm, which is like this so-called certificate problem, and focus entirely on this piece. And then, tell you why the kind of certificates that work for the vanilla planet click problem and people have studied for like decades don't actually make sense in this context. But there's a new geometric version of this idea that actually seems to make sense. Let me apologize in advance. I know you have, seen actual algorithms classes. This is the way of designing algorithms if you took a theory of computation class but did not take like an algorithms class. This is like, the complexity theorist way of designing algorithms where you first come up with an inefficient algorithm and then try to, I don't know, tinker with it to make an efficient one, okay? So apologies in advance, okay? Oh yeah, this is from the time when, the AI tools were not so great. So they misspell, theory of computation. I hope you don't mind.
They still do.
They still do? Okay, sorry. I just assumed that there's been a few weeks, so. All right.
I'm just paying $20 and nothing comes.
Yeah,
Okay.
I created a PDF mesmerized and asked you to generate an image.
Yeah. This is what happened?
Things like this.
Okay. All right.
It's a little bit better than before.
All right. Excellent. Let's see an inefficient algorithm, okay? This is something that we can reason about together. I know it's like early morning, but you've got coffee. Let's think about it together, okay? So suppose, we don't care about running time. Okay, your goal is to find me a short list that is guaranteed to contain S star, okay? What would you do? So, one thing you could hope to do is, say, okay, there is no constraint on running time. I can find, clicks very easily. Maybe I'll just enumerate over all possible k clicks. It's got to be S star in them, but this doesn't work. Right? This strategy doesn't work because V minus S star could be one giant click on its own, and then there are exponentially many k clicks. I only want n over k, right? So you see, like at least even in the statistical problem, there is something interesting going on in the sense that you have to think at least for like a couple of minutes to understand how you might solve this problem, even if you had no running time constraints.
The cross graph.
Say it again.
The cross graph is special, right? Between S star and V star.
Exactly. That's the only benign part. So of course you have to use this, and Raghu is saying how this proof is going to work already. So right. So let's see what the idea is going to be. Let me just describe the idea in the following way. What I'm going to do is like I'm not going to enumerate all k clicks. That's not a good idea. Instead, I'm going to enumerate clicks that satisfy some extra property coming from like this cross graph or cut like Raghu was suggesting, with the idea that I make sure that S star, my good click, satisfies this property, while also arguing that in every graph, the number of such good clicks are not too many, are exactly at most n over k. If I can find such a property, then I'm done. Yes? Excellent. So, let's identify this property, and you can almost see why this is a theory talk. Look at how imaginative my name for this property is. So, I'm going to call such clicks good clicks, okay? I'm going to call a k click, L good if it has the following property. If I look at any other k click in the graph, the intersection between this k click and my click, right, should not be more than L vertices. Okay? So a good click in other words, is like in some sense almost disjoint from every other k click in the graph. Okay? Sound good? Okay.
L to be less than half the size.
Yeah, exactly. What L we want is exactly what we are going to worry about. Right now it's like an abstract, but yeah, we'll come back to your question.
Can we log in, right?
Yeah. Yes. Well, we don't have to come back to your question now. Excellent. So, this is the answer to your question. We'll in fact argue that if we choose L to be like some constant times log n, then the planted click S star is L good, like or a log n good, right? And this proof is actually very simple. This is just, just arguing by some Chernoff and union bound over all possible, whatever possible k clicks that, the intersection cannot be large, okay? So it's something that you could give like an exercise in your first probability class or whatever. But because I've got to toy with you a little bit, I'm actually going to belabor a proof of this. Okay, now there is a real reason. I'm going to belabor a proof because I'll try to do it in a way that suggests what to do, going forward for the efficient algorithm part, right? So even though this is easy, I'm going to give you like some framework for thinking about it. Okay, so let's think about it. Suppose S star is not L good. What does that mean? It means like there is some other k click in the graph that intersects S star in like at least L vertices, okay? Here is how I'm going to think about it. I'm going to think about the bipartite graph between S star and the rest of the vertices, meaning I'm going to ignore the edges that are internal to S star or V minus S star. Okay? Notice that in some sense there is very little information there, right? V minus S star was worst case, S star is clique, whatever, I'm going to ignore it. Okay? So the only edges that basically I'm looking at now are in the cut of S star, right? What does it mean that there is a clique that intersects S star in L vertices? Well, there is some T, right, which has like the T intersect S star part on the left of this bipartition and the rest of the vertices on the right, and crucially, because T is a clique, right, this two-way partition of the set T is in fact a bipartite clique in this graph. Okay? Okay, very good. So it's a L by K minus L by clique. Okay? So very good. So now imagine that there is no deletion. Eventually, like you'll see why deletions don't matter, but imagine that in the cut S star there were no deletions, it was just a random graph, right? Then we are basically asking in a random bipartite graph, right, is there a a large bipartite clique? But crucially, we are asking something in the very unbalanced regime where we expect the left side to be very small and the right side to be big. So that we are asking the question of is there a unbalanced biclique in this random graph? Okay, so you can argue this quite easily by just Chernoff and union bound, and you can also observe that if I delete edges, it can only help me in this. I can't create a clique if there wasn't one before. Good. All right. So now you've seen a proof. Okay. Let me tell you why this immediately implies a inefficient list decoding algorithm. Okay. The idea is very, very simple, right? I have to argue that so I argued to you that S star is L good. I need to prove to you that there are not too many L good cliques, right? K cliques in this graph, right? And this is by a shout out to Arya. I thought Arya is going to be in the audience. I also assumed he was the chair. Sorry, Raghu. So I thought I'll phrase everything in coding theory language. Okay. So there is a different version of this talk where I say something else. Okay. But this time I'm going to use the Arya language. So if you've seen this decoding of codes, okay, then basically what I'm going to use is the so-called poor man's Johnson bound. It's poor man's because it's like a very weak version of it. It basically says that if you have here it's like very simple. It's like if you have almost disjoint K cliques, right, and you try to count how many there can be, then there cannot be too many. And if the argument is just one step of inclusion exclusion, right? Like you say, well, if I have a bunch of K cliques that intersect very little, on the one hand they cover too many vertices, but their intersection cannot be too small, but then you'll have too many vertices. It's a very simple argument. Here is the argument. It's like exactly 2 lines, but don't read it. Okay, it's an exercise. Okay, so what does this poor man's Johnson bound tell you? It basically says that as long as you choose K to be larger than, let's say, some square root of n times L, so if L is log n, this is like square root of n log n, then the list size is like no more than 2 times n over K, and this 2 is just for my notational sake, you can make this 2 like 1 plus little o of 1 with not that much effort. Okay, so makes sense, like the inefficient algorithm? Excellent. So we have solved the information theoretic problem. Let's now try to make it efficient. Okay, good. So technically this algorithm might run in exponential time, but you can be a bit clever and make it quasi-polynomial too. So the brute force algorithm here is still quasi-polynomial. Of course, we are going to be interested in polynomial time algorithms. Excellent. So the key to this inefficient algorithm of ours was this problem of verifying that there is no large unbalanced bipartite clique in this random bipartite graph formed by S star and the rest of the vertices. Okay. So it turns out that even for the efficient algorithm, this is the key, but I'm going to phrase an algorithmic variant of it. If you haven't seen such problems before, I'm going to define a concrete one very soon, but it's the question of, given a random bipartite graph, one way you can check that there is no large biclique is by just going over all possibilities, but this is going to be at least quasi-polynomial time because, you have to like enumerate over all possible log n subsets of the left hand side, right? But I'm going to ask you, is there like some short witness you can give me, short proof you can give me, such that if I read this proof, right, then I'm convinced that there is no large bipartite clique in this graph. This is called a certification problem, right? And I'm going to phrase a concrete version of it this way, okay? Now, for the rest of the talk, you can just think about this problem, okay? Because I'm not going to tell you anything else anyway. So, your input is an arbitrary K by N graph, okay? In your mind, think of it as S star versus the rest, okay? Your output is a number between 0 and K. Think of it as like the upper bound on the left hand side of the maximum biclique. Okay? So, the algorithm you develop for this problem, which takes K by N graph and outputs a number, should have the property that if you output some number L, there should not be a L by K biclick in this graph. Okay, so far the first three parts are completely worst case. Okay, there is nothing average case about this. This is a worst case problem. The only way, but also you can win the game very easily by outputting L equals like I don't know K, right? So the way the problem becomes interesting is I ask you the following additional property, that if H happens to be a random bipartite graph, the kind that we expect cut of S star to look like, then you should output a small number. Okay, you should not output something huge. So of course, we can expect to output some number which is order of log n. N to the epsilon is something that I'll be happy with. Don't give me something like that compares to square root of n. Okay, good. So this is the problem of refuting unbalanced large biclicks in random bipartite graph. If you I don't know if you've seen like such problems before, but the heart of like the planet click algorithm is also an algorithm of this sort, but where the input is a random graph, not a random bipartite graph. And in fact, random bipartite versions of that problem are also studied, but for some reason, nobody looked at like this unbalanced version. Like when they looked at the bipartite version, they looked at like balanced bipartite clicks, but somehow the key to this semi-random problem is this unbalanced version, which in principle, at least to me, seems like a problem you could have studied on its own sake, even if you never learned about the semi-random click problem, which I assume you will believe because this is all I'm going to tell you for the rest of the talk. Okay, excellent. So like we saw before, you can just brute force out and give a quasi-polynomial algorithm to solve this problem. Just check all possible log n subsets, right? Good. Oh, I guess this I already argued to you. So it turns out that if you solve this problem, then there is in fact an efficient algorithm. I'm not going to tell you how. This is where sum of squares plays a role, but this is also like in some sense entirely black box. Okay. So in Arya's language, one could say that you can basically make this poor man's Johnson bound essentially algorithmic. Okay, so if you can solve the certification problem efficiently, you can also basically enumerate the list just like we expected in the inefficient algorithm. Okay, so I'm not going to tell you how this works. I'm going to ask you to take it on faith. Okay, good. So good, yeah. This builds. Making this algorithmic requires like all this work in list decodable learning, but it's all done for us. So good. All right. So now let me tell you, how to solve this certification problem. First, I'll tell you, or at least quickly sketch for you why the usual certificates that we are very familiar with don't quite work. And then tell you why some new kind of certificates will save the day for us. Okay, that time is right?
Yeah, that's right.
Okay, good.
The balance problem was solved in a very different way for the certification thing.
Yeah, I'm going to actually tell you how to solve it, right? Like somehow, So this is the point I'm going to make. When things are balanced, it turns out that the spectral certificates, which are very natural in this area, work very well. And so people thought, well, okay, we are done. But it turns out the spectral certificates fail, and I'll also argue to you, all like 2-line proofs. But then we'll see a new like geometric way of thinking about this problem and solving it. Yeah, because I'm doing so well on time, I can take more questions. Okay, good, excellent. All right, let's do it. Okay, let's think about spectral certificates and how people thought about these certification problems before. Okay, so. First, I'm going to tell you the following, okay? First, I'm going to tell you how the random graph version of the problem, not random bipartite graph, but random graph version is in fact solved using some efficient spectral certificates. And if you haven't seen this before, take it on face value that this is somehow the heart of, in some sense, the Alon-Krivulevich-Sudakov algorithm that works at square root of n, okay? Here's the basic idea. The idea is that you can relate the maximum eigenvalue of a matrix associated with the graph to the size of the largest click in it. Okay, it's a very simple but nice and useful observation. Okay, so for any graph A, think about the matrix which writes +1 in an entry if there is an edge and -1 otherwise. Okay, then I claim that the largest click in such a graph is no more than 1 plus the largest singular value of the matrix A. Okay, and the proof is very simple. Okay, if you haven't seen this before, I'm going to tell you. Okay, here's the proof. Say x is some 0, 1 indicator of a k click in the graph G. Okay, you're just going to compute x transpose ax in two different ways. Okay, x transpose ax basically gets a 1 whenever ijth entry are both ones in x and there is an edge between them, right? So if x is an indicator of a click, you get that you basically have all possible whatever k times k minus 1 entries except the diagonal, so coming up +1. So the lower bound holds because x is a k click. On the other hand, you know, A is a matrix, X transpose AX is its quadratic form, so I can upper bound it by, you know, just a singular value of A. And if I do that, I get that, you know, I get an upper bound of K times the largest singular value of A. You put them together, you get that, you know, K must be at most 1 plus the spectral norm of A. Okay?
This is also very similar to Plotkin bound. If you know the.
Oh, really?
Yeah.
You're saying I could have like made another.
Said that as well.
Let's talk. Okay, good. So this is very nice, very you know, very cool. Why is it useful, right? Like maybe the spectral norm of A is huge. Here is the observation. If you know, oh, I guess I don't have the observation. Okay, whatever. Let me tell you the observation. The observation is that if A is the plus minus 1 adjacency matrix of a random graph, then you know we know by like some basic random matrix theory that the spectral norm of A is at most 2 times square root of n. Okay, this is the random matrix fact. So basically, you know, you get the upper bound in the random graph should be 1 plus 2 root n. Okay, so basically O of root n. Okay, so notice that how I would solve the certification problem. I'll just, you know, take the graph, build a plus minus 1 adjacency matrix, compute its spectral norm, and return 1 plus that number. This number is always an upper bound because I argued the worst case version to you. But if the graph happens to be random, it's going to be order of root n. Okay, so this is like a solution to the problem, and this is also the heart of, like, you know, the AKS algorithm. Excellent. So you know, you can ask what happens if I try to do the same kind of argument for the unbalanced bi-click case. Okay, so actually, you know, something very similar works. Okay, so you know, think of like, you know, L and K as like the left side and the right side of the click, right? If they were both the same, LK would be about K square, right? And then you get an upper bound that K square is at most, you know, the square of the spectral norm, so K is at most the spectral norm, which is like the previous slide. But the key or the bad part is that when L and K are very different, you get basically a terrible bound on L. You only get, if you like, you know, so I'm going to hide it because it's the same proof, but if you like work it out, you know, you plug in the bound you get from here, lo and behold, you basically solve the semi-random click problem when K is at least n to the 2/3, okay? And this is basically the reason where n to the 2/3 come from. It looks like a funky number, but this is the reason, okay? Because at the heart of it is a spectral certificate, okay? So, you know, you might wonder that maybe this is not the best way to do the argument. It turns out that you can prove, and we did, that the basic SDP for this problem of certifying unbalanced biclicks in fact does have the integrality gap that corresponds to the n to the 2/3 number. So at least you cannot use degree 2 SDP to beat this bound, okay? So, you know, you could think of this as like the implicit reason for the barriers in the prior works. Good? Any questions? Excellent. Good. So now I'm going to just, like, you know, claim things on some like thing that you were supposed to take on faith. So, you know, you could try to build other matrices, and we did for months, and it turns out that, you know, they also fail. Okay, so you might think I'll try to rescue this by some bigger matrices. Turns out like natural bigger matrices where you try to somehow construct spectral certificates from doesn't seem to work. Okay, good. So finally, you know, I'll tell you what works. Okay, which is like, you know, this idea of thinking of geometric certificates. So you know, this is completely standalone, and I hope that, you know, in the next 5 minutes I convince you of how this works, because it is very, very simple, but I like it a lot. Okay, good. So here is the fact I'm going to show you. Okay, so it's a completely standalone lemma that I'm going to actually prove to you end to end. Suppose you take a random k by n bipartite graph, the kind that we are looking at so far, and suppose there is a L cross k bipartite click in this graph. Okay, then from the existence of a L by k biclick, I will extract L choose t vectors in Rn, okay, such that the pairwise inner product of these vectors is negative. Okay, this sounds a bit weird. Why would we do this? So, you know, let me see if, you know, some people have seen like this easy but very nice fact. In n dimensions, how many vectors can I possibly have which are all pairwise negatively correlated? It's also a coding theory fact.
Yeah.
Goes into the proof of Johnson bound.
Yeah, exactly. So, you know, you can only have n plus 1, okay, and they are the vertices of the simplex. So, you know, you cannot have more than, you know, n plus 1 vectors which are all pairwise negatively correlated. Why does that help? Well, I'm saying if there is a large biclick in a random graph, then I will build, you know, lot of pairwise negatively correlated vectors. On the other hand, there cannot be too many, so I put those two together and I get that the smaller side must be n to the 1 over t, where t is like any number less than equal to L. I'm really like singling out this parameter t because eventually the running time would depend on like t as the exponent. Okay, so of course I could have just done like 2 to the L bigger than 2 to the L bigger 2 to the L at most n plus 1 would have like be a reasonable argument, but I want to like parameterize it by like this t. Okay, does the statement of the claim make sense?
Where is the t coming into play here?
Yeah. So it's not coming into play here at all. Like this claim is true for every t. So like you're observing, I could have just used, I guess, t equals L over 2. Or really, I could have taken like really all possible subsets of like, L.
Is it going to show up in the degree of your...
It's exactly, it's going to show up in the running time of the algorithm eventually, okay? There is another cheating I'm doing on you at the moment, so you should like try to keep me honest eventually, which is that this statement doesn't make sense because I need like some deterministic property, right? Like what does it mean that suppose there is a L by k biclick in a random k pi n? I mean there is no, we know it, we proved it, right? So eventually I'm going to replace random k by n h with like some deterministic properties which are easily testable in the graph. Okay, so eventually it will be a statement about all graphs that satisfy some property which is true of a random graph. Okay, so we'll get there, but right now we'll keep this lemma in this slightly useless form for now. Okay, good, excellent, let's do it. Okay, so yeah, so t comes in because there is an algorithm that comes out of it. Okay, good. So I'm going to construct these vectors for you. It's very simple. Okay, suppose you have this L by k biclick in this random bipartite graph. How am I going to construct the vectors? Here's what I'm going to do. I'm going to define the so-called parity neighborhood indicator. Okay, here is what it means. I'm going to choose a subset of vertices on the left hand side. Let's call it z, right? Now for each subset z, I'm going to build a vector whose dimension is the size of the right hand side. Okay? Yeah?
Subset of the fixed size or no?
Subset of the vertices.
Yes,
Fixed size. Yeah, eventually it will be of size at most t. Okay, but right now like think of it as like an abstract size. Okay, we don't care about the size at the moment. Okay? So z is any subset of vertices on the left hand side. I'm going to build a vector with dimension size of the right hand side. And what do? I basically take so I have to there's one coordinate for each vertex on the right hand side. So let's say j. So I look at all possible edges or potential edges from j to every vertex in z. It's like size of z many possible edges, right? I take I basically multiply the plus minus 1 indicators of these edges to get this vector's entry at j, right? So basically it's counting, are there odd number of edges between j and z or even number of edges between j and z, and like taking some plus minus version of this. Does that make sense? That's the parity neighborhood indicator. Okay, good. So that's basically how it looks. Okay, good. So what's true about parity neighborhood indicators? If I take two distinct subsets z and z prime, right, and take the corresponding parity neighborhood indicator vectors and take the inner product, I hope it doesn't come as a surprise for you that the inner product is basically going to look as if they were random vectors. Okay, they're not, they could be correlated, z and z prime could intersect, but as long as they're not the same, their inner product basically looks like like random random vectors, and it's going to be like square root of n, and then root log n comes by just some union bound business. Okay, any questions about this? Feel free to ask me. I'm doing well on time. Yes, I absolutely can. Okay, so here is the definition. Okay, so what am I doing? For any subset z of vertices on the left hand side, right, I'm going to define a vector n sub z, which is a vector whose dimension is the size of the right hand side. Okay, so there is one entry, one coordinate of this vector for every j on the right hand side. So if I fix a j, here is the entry, like here is how I decide the entry. I look at all possible connections from j to vertices in z. There are z possible of them, right? If there is an edge, I'll think of plus 1 on the edge. If there is a non-edge, I'll think of minus 1. I just multiply those out. Okay, clear?
So it's like you have u, and then you are taking all L size subset and computing their parity. So it's like
so t size actually, but
sorry,
yes,
T size,
right.
So it's like a parity check.
Yeah. It probably also has some coding theoretic interpretations. You're saying I did not do my job well enough. That's basically what you're pointing out.
You mentioned parity, so I'm just...
This
Yes.
is what's similar for planted click. There's this paper of Fries and Wemperle where they say that if you take
That's a triangle thing.
What?
You're talking about like this, the
Basically,
tensor.
tensor, yeah.
Yes, yes.
They also look at subsets and they look.
They also look at parity, but they form like a degree, like the goal is different. You form like, instead of a quadratic polynomial associated with the quadratic form, you form a cubic polynomial where the coefficients of I, j, k are like the triangle parity indicators. And then they prove that, this maxima are correlated with the clique whenever the clique is larger than n to the 1/3. So yeah, the parity enters the picture, but perhaps not in the same way, okay? Good, so far, I've given you some vectors, right? So, and I told you that, in a random graph, no matter what z and z prime are, as long as they are distinct, the inner product is like basically like random n-dimensional vectors. So like root n or root n log n, right? Good. So this is the only property of H I'm going to use, okay? So I can replace whatever like a random k by n H in the hypothesis of the lemma by basically like, saying that for all z of size at most t, if I take like distinct z and z prime, take the inner product, the corresponding parity neighborhood indicator product, right? Then it is basically like random vectors, like root n. So this is,
T comes to the exponent.
Yes.
And then you set T to the
because checking this is going to require like going through all possible subsets, so it's going to like, require me in principle n to the t time, okay? At least if I don't try to be super clever, which I'm not going to be.
What is this robust to deletions?
We'll come to it. Yeah, Raghu is saying like a few slides ahead. Actually, he's saying at non-existent slides, but
Hope is there in the paper though.
okay, good. All right. So this is all you remember, right? Like this is all you remember from the construction so far. So now we have pairwise almost uncorrelated vectors. That's one way to think about it, right? And you might say, well, let's, before going to negative, let's ask, is this enough? How many pairwise like almost uncorrelated vectors can there be in n dimensions? Exercise exponentially many, okay? It's not a hard thing, it's a very easy thing. So this is not going to win for us. I've got to do something else. Here's what I'm going to do, it's very simple. I've not used that so far that there is a clique, right? So far this is all just abstract nonsense, right? Okay, let's use the fact that there is a clique, okay? Imagine that Z is a subset of this purported bipartite clique, okay? So Z is subset of this L part on the left, okay? Then, there is some right part of the clique of size k, right? And let's say those are the green vertices at the top. And to all those green vertices, every vertex in Z will have an edge. So what happens if I take the parity indicator of such, j's? Well, all of them are +1. So the green vertices basically contribute a +1, right? So in no matter what n sub Z is, I have like, in this green part, +1, +1, +1, +1, right? So what is the contribution to the inner product from the +1s? Well, there are k of them, so they contribute a +k. Okay, great. So what happens if I strip off the green part from each of the nz vectors? Well, before stripping off, the inner product was at most root of n log n, but apparently this green part contributes +k. So the inner product should now be, root of n log n minus k, and if k was like larger than order of root n log n, then this is negative. That's it, we are done. I've constructed for you a bunch of pairwise negatively correlated vectors. Now you just apply like the simple geometric fact and go home. Okay, good, that's it. So just to summarize, here is the solution to the certification problem, right? You were given a k by n bipartite graph. You basically compute all possible n sub z's, okay, of some size t. Check that, for distinct z and z primes, the inner product is as in random, right? If not, you just say whatever k, right? If it doesn't satisfy this balances condition, you just like say, okay, I don't know what graph you gave me. I'm not going to commit to anything. I'll give the largest possible L so that I don't, fail the correctness test. But if this test is satisfied, we already proved that there cannot be a large clique in any graph which satisfies this test. So, if this test is satisfied, I report, whatever, n to the epsilon, right? Good. Any questions about this? So we've solved the certification problem, which is a little bit of a bait and switch on you because you started with the goal of solving the semi-random clique problem, but this is all actually I'm going to show you. So yeah, that's all I have. I'm going to like tell you some takeaways and then try to answer Raghu's question. Okay. Okay. So basically, we can basically like get or at least approach the threshold for the average case problem. So maybe like the one meta message is that even though there was semi-random adversary, there is like a new heuristic, like this whatever, the SDP that comes out of like this certification whatever, that seems to be slightly more robust, right? Like it doesn't seem to utilize the randomness of the graph in the same way, seems to be slightly more robust, which is quite nice. Of course, there's a natural question of whether we can do this, at root n polylog n. right? We only got it at n to the 1/2 plus epsilon so far. I also like it. I know this is like more speculative, but I somehow like the message of this thing. Like think about the worst case k-click problem and think about like what perhaps makes approximating clicks in graphs so hard. It's like basically in some sense the hardest approximation problem, like where the best gap best algorithm basically achieves like some factor n over polylog n approximation, right? So it's like a ridiculously hard problem, and you can ask where does the hardness come from? Like I don't know, in some speculative way, right? And we're saying that okay, in some sense, if the click cut is random, then that graph is easy, right? That's basically what we just proved. So in some sense, all the hardness of the solution concept of clicks is in like the cut of S star. The rest of the graph somehow doesn't matter. It's like a way of looking at the same result, but I find it somehow insightful. Yeah, you saw the conceptual key. High degree SOS somehow helps, and might be good to get out of a spectral mold, which is a mold that people often are in this world. Good. Okay. So let me end with some future business, right? So you can ask, can I do root n polylog n? I got n to the 1/2 plus epsilon, and it turns out that in this model that I did not quite define to you, but it has like slight easiness, and the easiness is that you're not allowed to delete edges in the cut. Like everything else is the same, but you can't delete edges in the cut. For this model, it turns out that there is a different algorithm that we now have, which actually succeeds at k equals root n polylog n instead of like n to the 1/2 plus epsilon, and this one's in some fixed polynomial time, in fact some n cubed time. So yeah, so and then it comes out by some new connection to the RIP property, if you heard about it. So that's but we somehow don't know how to make it work in the stronger model yet. Okay. There is a even harder semi-random model that Feige proposed in this his chapter on this Beyond Worst Case Analysis book, which I'll basically dump on you. He says the following. Okay, take an arbitrary graph, worst case whatever, right? Take random k vertices in this graph, complete the click on them. Okay, that's it. And the question is find a k click in this graph, or I don't know, k to the 0.99 size click in this graph. So basically, why is it different from worst case? Because the choice of the k vertices that I'm putting a click on is random, but that's the only random part. Okay. I asked Feige. I mean, I always think of it as an algorithmic question, but Feige believes this is hard, so he was asking in the sense of like prove hardness for this. So you can see that there is controversy already. Good. So and finally, like I don't know if this is IPAM, so there is M at the end. So I'll tell you like some M question. So I don't know if you know this problem, but there's a very nice problem of like understanding the Ramsey properties of this very specific graph in number theory called the Paley graph. How many of you have seen the Paley graph before? Okay, very good. Some of you have, right? So Paley graph is basically like a graph on the first 10 integers where you connect, or let's say let's numbers numbers mod p or whatever, where you connect two numbers if their difference is a square, like it's a quadratic residue. Mod p, yes, yeah, we're in, let's say, some field f sub p. There is a sense in you can define it over z mod n2, but let's say over f sub p, okay? And this graph is when you are in prime modulus is conjectured to be Ramsey, as in like it doesn't have like a large independent set or a click. In fact, people think of it as like a deterministic counterpart of random graphs, gn 1/2 for like many purposes. And so the outstanding question is like, what is the bound you can prove on the click number of this graph? It's symmetric, so click number implies independence number 2. The square root p, the spectral certificate, it turns out generalizes here. So you can actually get a square root p bound, which is like the analog of gn 1/2 I proved you. But people conjecture log, that's maybe reasonable. And just to tell you how desperate we are, about 3-4 years ago, there was a big breakthrough in this area. And the big breakthrough was proving a click number bound of root of p over 2. Okay. So shaving off root 2 was the big breakthrough. The best result before this, I think, was like, square root p minus some 2 or something. So like people have written papers for like additive changes, and multiplicative change was like a big breakthrough. Yeah, so I don't know, like I wonder if like some of these certification ideas would lead to some interesting thoughts on Paley graphs. Okay, that's all I have. Okay, so there's like a meta message, which is like which is somehow like some description of some of the things I've been trying to do over the last few years. Which is like take some of these methods that we know and understand for average case problems, not just like commutal optimization, but like I don't know, many other problems in learning or whatever. And like try to somehow reduce randomness, try to make the model less and less random, more and more like somehow closer to worst case. Of course, you can't, in some sense, you can't expect in these problems to go all the way to the worst case, but somehow the idea is that we should try hard to reduce the distributional assumptions in our algorithms, try to get as far as we can, and often there is a way to somehow think of our algorithms and refine them so that we use less and less of the assumptions. I think it leads to more robust algorithms and some beautiful new connections to math, and yeah, it's worth doing it. Anyway, all right, that's all I have.